Okay, so let's pick up back from the point we left off last time. So we talked about the staggered conformation for conformers. Now let's talk about the eclipsed form. Okay, so the eclipsed form is when we're looking at the molecule. So we still have CH3. Well, let's draw that in our different structure formats. So if it's eclipsed, the H's are going to be oriented in the same directions on both carbon atoms, and they're going to look like they are directly in front of each other, like a eclipse would be, such as a lunar or solar eclipse. So here's my dash wedge drawing. And then if we look at one of its ends, so let's not draw it that way. Okay, let's redraw that. And we're looking on this end. Okay, looking down that axis, we can see here that the H's in my sawhorse drawing are going to look like this. Okay, both atoms are now eclipsed. Both carbon atoms and its groups are now fully eclipsed. So this will be the sawhorse. And then we have the Newman projection right over here. And you see the hydrogens are fully eclipsed in this position. Okay, so the staggered forms and the eclipsed forms, they're different energies. They have different stabilities. So one is more stable than the other, and there's a few factors that contribute to this. So let's draw a line under here, and we'll talk about the first one. The first major factor to why eclipsed is not as stable is torsional strain. So torsions or torsional strain refers to the repulsions between the eclipsing groups here. Okay. So from this position, you will see an increase in energy, or the change in energy going from staggered to eclipse is an increase. So an increase in energy from the rotation of the sigma bond as we go from staggered to the eclipsed form. From staggered to the eclipsed form, as in a solar eclipse. Same kind of concept. Alright. So this energy is called the torsional energy. So in order to rotate and arrange the atoms this way, this is called the torsional energy. Okay, so let's look at a molecule like butane. So if we look at butane, okay, so we're gonna have butane here. Butane as my example. Each time these atoms rotate, or the atoms as they rotate around the bond, these eclipsing interactions will have varying the amounts of energy. So depending on what atoms are trying to rotate past one another, the energy will be different for each. So let's make a little chart here. Torsional energy between two groups. Okay, so if you have an H interaction here, the energy is 1 kcal per mole. If there's a CH3 in an H group interacting, it's 1.4 kcal per mole. And then you have two CH3s interacting. It's going to be 2.5 kcal per mole. Okay, so let's look at an example when we're going from staggered butane and eclipse butane. Okay, so in this case, we're looking down this bond. So we go 1, 2, 3, 4. We're looking down that bond. Maybe I should let's just draw it this way. Since we're looking at the 2 to 3 bond axis. Okay. So, actually, let's go back. Sorry, guys. Let's go back. Let's just draw it this way because it's positioned better in this case. All right. So, if you look at the front carbon, so in that case, let's just erase these numbers. Let's just redraw it really quick. 1, 2, 3, 4. Okay. So if we look at the 2 to 3 bond, down that bond, my front carbon will have a methyl group coming up, as indicated by carbon 1. And then on the front here are 2 hydrogens that are not explicitly shown. And at the back carbon, carbon 3, there is a methyl group pointed downwards in the back. So that's the outline of the circle. And then we have 2 hydrogens coming out like this. Okay. So this can be said to be in equilibrium with its conformer when the back carbon rotates 60 degrees counterclockwise. So let's draw that Newman projection right here. So we have a CH3, H, and then all right. Well, I guess this is 120 degrees. So we rotate. So we're gonna rotate 120 degrees. So you rotate the back carbon 120 degrees. Counterclockwise, you would get this eclipse conformation on the right. Okay. So what happens is that if you go forward, this will actually require 4.5 kcals of energy in order to get to this state, to this eclipse form. Okay, so that tells us that the eclipse form is less stable because it requires energy to get to that state. All right, staggered is the more stable because most of these molecules will be in the staggered state because it has less energy. So when you have less energy in chemistry, that means you are more stable. You don't want to react or change or do anything like that. Okay? So if we notice here, there are one CH3 interactions here. So one CH3 strain because of the torsional strain. And then you have 2 times HH interactions here. So if we use our chart on the left there, we're going to have 1 times 2.5 kcals. Okay, 1 times 2.5 plus 2 times 1. And then we put that together, that will give us 4.5 kcals. So that's where the strain comes from. Each of these interactions is giving this molecule a certain degree of instability here. Okay, so now let's, in lab, we kind of went over this in more detail last week, but let's redraw this graph to make sure we're all on the same page. So let's draw a line under here. So we can actually graph how these conformations are changing to one another using this graph that I'll draw right now. Okay, so on the y-axis you have energy, and this is going to be kcal per mole. Typical energy unit. Okay, and then on the x-axis right here, you're going to have torsional angle. So this is the angle of rotation of around that central C-C bond. Okay, so let's draw let's draw a graph here. So we're going to draw a graph like this, and then draw the right end here a little bit higher than the left. And then this is going to go into a bigger curve here. All right, then the same curve there. And the same height of this peak here as we had at the start. And then this is going to end right approximately around the same end of this line. So let's draw these lines under here to indicate that these are conformations. Okay. So let's draw a dotted line to the end here to indicate the relative heights of these conformations. Okay, so the first conformation on the left and the right, they are equivalent. Okay. All right, these are the anti-conformers, where the methyl groups are on opposite sides, so they're furthest away from each other. So here, this is going to be for butane. So the conformers here look like that. So you're going to get 2 of these, 2 kind of conformers where the CH3 groups are on opposite sides. This is called the anti-conformer, so ANTI conformer, and that's because the methyl groups are opposite from one another in space. All right, so let's draw the other one here. CH3. Okay. So these 2 positions would be when we did not rotate at all, so at 0 degrees rotation. So this is a degree angle. And this is when we made a full revolution, 360 degrees. So those 2 conformers should look the same. They're the most stable because they're the lowest energy here. Now we rotate the back carbon by 60 degrees. We get the first eclipse conformation right here. And the eclipse conformation is higher in energy than the the most stable staggered conformation by a certain number of energy units, which I'll go into. Like so. So the height of this peak, this is going to be activation energy 1. So the amount of energy it takes to achieve this rotation, this is 3.8. And the units here are in kcal per mole. Okay? So once we rotate, get to the eclipse conformation, it requires a bit of energy to do this. And then once it rotates again, another 60 degrees. Okay, so this will be 60. Now we'll go another 60 to 120. This conformation right here is it's a staggered conformation, but it's not as stable as the other staggered conformation, because the methyl groups here are now close in proximity to each other, so there's going to be some interaction there. That's why the energy is slightly higher. And we can see here that the energy of this distance to this dotted line here, this is 0.9 kcals. So very small, but still a difference. Okay. Now when we rotate that another 60 degrees, okay, now the methyl groups are going to actually be in close proximity to each other. So now let's draw the front carbon. And now we're now going to get another eclipse conformation, and the methyl groups are going to be close together now. So see, the methyl groups are eclipsing. Now if we draw the height of this peak to not the dotted line below, but the dotted line where it reaches this point where the 0.9 is, okay? So we draw the distance between the starting point, where 0.9 is, and the height of the peak. All right, this is activation energy 2. So this is going to be, it looks like it's not bigger than activation energy 1, but that's because the starting point is a bit different than the first one. Okay, so that will take 3.6 kcals per mole. So we could put kcals right here if we want. Per mole. I don't think I can fit it over there, but the units are kcals per mole. Okay, so then once we rotate there, we get another gauche conformation. So the stagger conformation where the methyl groups are close, but they're not eclipsing each other yet. Okay. So it's on the other side of the methyl group. There we go. Bam. Okay. So now if we rotate this another 60 degrees, we get to the last conformation, which is now this distance. So let's draw a dotted line here. Okay. And we draw this dotted line here. This will be activation energy 3, and it's this distance here. And since the starting point is not the same as the first activation energy, this energy will also be slightly different, 2.9. Okay, and then we will start here, and we'll start to draw these eclipsing conformation, and then we'll continue on in I have another video here where we'll continue with the rest of the lecture here. So CH3, H, H. All right. Yes, it's working. All right. Sorry about that hiccup. Well, I guess a nice little breather there. So, you see how we rotate all the bonds there, and the energy is changing accordingly. All right. So to kind of put this in perspective, let's watch a little show a little clip. Yeah. What's up?
Why is activation energy 1 higher than activation energy 2?
Oh, okay. So that's a good point. But we got to remember that EA of 2 is just from this top right here, just to this bottom right here. If you notice the EA1, the arrow is actually pointing to the level of the anti-conformer, this one right here. Okay. So the reason why it's lower is I haven't included in this number the 0.9, whereas EA1 has that 0.9 included. So the actual there's two different initial points, right? The initial point for EA of 1 is this bottom right here, and then for EA of 2, the bottom is this elevated position right here. So notice that they're not the same level. So EA of 2, if we have the same initial, first point, it'll be 4.5 kcals. So it's actually higher. But I want you to realize that as we go from left to right, we're considering the height from the point on the left. Okay. So from this point, we're considering the height to this point, and then from this point, it's this height to this point. So that's how you calculate activation energy. Is the reactant before it, activation barrier, then to the product that's on the right. Okay, so if we were to annotate, so imagine this is our reactant, right? And this is the intermediate. These are the intermediates, okay? And this is the final product, which they are the same thing because we're just rotating the molecule. So it's not actually like a chemical reaction per se. All right. Any other question? That's a good question because when I was going through this again, I was like, wait, why is this one lower? But I forgot the 2 points on the left and the right. They're not the same. All right, so to kind of see how these molecules rotate, let's look at a little video over here. All right, so conformation analysis. So I have these, there's a YouTube playlist for this app. It's on the Apple Store. I used it a lot when I cheated at Davis. But it's a good like kind of companion app. With lots of videos and visuals to kind of help you get through this class, okay? Most of the concepts. So let's look at butane, because that's the one we drew. All right. So if we play this movie, all right. So you see how it's rotating, and as it's rotating, it's cycling through this graph that we just drew. So what's happening is as the rotations are going around the central bond, you can see how the energy changes. All right, does that clear up any misconceptions? If not, you can review this video on Canvas. Okay, I posted a link to these. Hopefully it's as easy to find, but if you need help, let me know. All right, so the end. It's also narrated, so you can also listen to a narrated version too, just in case, you missed what I said. All right, so let's exit that here. Let's go. Well, you don't have to reproduce the graph, but you should be able to say, okay, here's this conformation. Please draw the conformer. If I rotate it, 60 degrees, 120 degrees, 180. Well, it's probably 60 or 180. In my opinion, because those are the easiest to draw. All right, so that's torsional strain. Any other questions on torsional strain? A little loopy loop here. All right. So I wish that was just the only strain in butane, but there's also what we call steric strain. So let's go over that. All right. So what's the difference between steric strain and torsional strain? All right. So torsional strain makes sense because it's repulsions because of the two sigma bonds coming close together. So that's torsional strain. Steric strain is like, you're in a traffic jam. You can't get through because if you try to get through, you're going to feel some pushback. Namely, your car is going to get damaged. Okay. So steric strain, I would say, is the repulsive interaction that occurs when atoms are forced closer together than their atomic radii allow. All right, so that means basically they get closer together until the point where they clash and they can't get any closer, basically. Okay, so we call this. There's a special term for this called steric hindrance. All right, so this is another type of strain, okay? All right. So let's go through all the conformers we just saw in the previous graph. And let's name the conformers, rank their stability, and list the strain, the kind of strain involved in each. Okay? So we have conformers of butane. All right, so we're going to draw our Newman projections as if we're looking down the 2-3 bond. Sorry, not 4. All right, so we have 4 conformations. All right, pardon my circles, not going to be perfect. All right, does anyone remember what we called this conformer? It's staggered, but which one is it? Has a specific name, special name. It starts with an A. All right, anti. So this conformer, letter A, okay? So anti is when the methyl groups are 180 degrees apart, okay? So, but what happens here is that the methyl group is going to feel some repulsion here from the neighboring H's. So I just drew one as an example, okay? So this is an example of steric hindrance. But it's not completely blocked, so we feel kind of a strain here, okay? And this is from the C carbon atom, the carbon on the methyl group interacting with the hydrogen on the back carbon, okay? So we see that interaction. All right, so if we interconvert 60 degrees here, we're going to get the first eclipse conformer. So this will be form B, conformer B, okay? CH3, H, well, I cannot draw straight lines, okay. H, and the methyl group is going to appear right here. And then the H right there, okay. Well, really bad lines today. Okay, so what's present here is steric hindrance. All right, we also have torsional strain. And this is mainly from CH bonds and H bonds, okay? So CH So you have torsional strain from CH, that's the major strain. And then steric hindrance is when these two carbon atoms, are closely approaching the hydrogens on the other carbon atom. Okay? So CH mainly is from these CH interactions. Okay, so we rotate that one more time, 60 degrees here, and we get the first gauche conformation. So this would be C, and this is called the gauche conformation, gauche. All right. Oh, I should have moved it though. All right. So let's rotate the back carbon 60 degrees. H3C. H. Okay. Sorry, let's remove that. All right. So what happens here is you're going to still see some interaction here. So the major strain in this one is steric hindrance again. Okay. And it's from this, now it's mainly from the C-C bonds from the methyl groups. They are now the primary strain in this molecule. Okay. And then lastly, we can draw the fourth conformation here. So let me just draw it first. So this one though, which one is this one? Which eclipse is this? All right. So this is going to be the eclipse conformation where which atoms are now eclipsed? Yeah, you got it. The methyls. Now they're fully eclipsed. Okay. So now this is even worse. They're closer together. See, I cannot draw those lines now. This is called the syn. So this is called the syn conformation. When the methyl groups now, the distance between them are essentially 0 degree, okay? No angle of separation between them. They're very close together, so that's syn, all right? So now we have the most steric hindrance. Okay? And we have torsional strain as well because they are eclipsing. All right, and this is from the CC, okay? So as we proceed to the right, the strain now goes from a CH interaction to now primarily CC interactions. All right, so be able to draw these conformers. Starting the homework, practice that we should use, okay? But are there any questions? This is the end, almost the end of conformers. Yeah, Catherine.
Conformer B, which of the hydrogen carbons in the structure are having the torsional strain?
Okay, so it's this carbon atom interacting with this one in the back, yeah. And then this one interacting with this carbon atom right here. Because they're close by because in space. So we're always referring through space, not necessarily through the bonds themselves, but their relationship in space. All right, good question. Are there any other questions on A, B, C, or D?
On D, can you go over the torsional strain one more time?
Yeah. So you see these two carbon atoms, right? They're eclipsing. All right. So when those two carbon methyl groups, so it's really this thing. So this bond right here, and this bond. So those bonds will be that will give rise to the torsional effect, torsional strain. Whereas the two methyl groups bumping into each other, that's steric strain. So there's both of them are present. That's why this one's the most unstable.
So that's why there's no torsional strain on the third one because they're not eclipsing?
Yes, exactly. Yeah, so you see in the non-eclipsing ones, there's only steric strain because of the group's proximity close to each other, the methyl groups and the hydrogen. But on the eclipsing one, you also have that, when they're eclipsed, that's the additional factor that makes it unstable. Yeah. Good. Okay. Now let's talk about the stability. So I'll ask you, what do you think is the most stable? All right, good. So the first one would be where the methyl groups are furthest away. That's A. All right, what comes next? What's the second most stable? All right, you got 3 options. 33%. I'm getting it right. What is it? C. Why do we say C and not one of the eclipsing ones?
Because everything is still relatively hard.
Yeah, so you don't have eclipsing strain, right? You only have steric hindrance, which is not that bad because it's still far away. All right, good. Now is the tricky part. Which one of the eclipsing conformations is more stable than the other? B. Okay, so the only difference between B and D is pretty much just the magnitude of the eclipsing interaction. And if we think about our values we saw before, a CC interaction is way greater than a CH interaction. So that's why we're going to list them as B and D. Okay? So B has the strain and steric hindrance through CH, but those atoms, C and H, they are not the same size, methyl group, right? And then in conformer D, the syn conformer, sorry, I didn't put D, let me put the letter D right here. That's the D conformer, okay? The syn conformer, the 2 methyl groups are bumping into each other. So that's the difference there. Catherine. No. I wish there was, but no, there's not. So B you can call, just the minor eclipsing one, I guess. I guess it's the eclipsing conformation where the CH3s are not eclipsed. I wish we had a term for that. Okay. Any questions about that one? All right. Now I might think we're done, but there's one layer we could add to this. What if I asked you to name a compound, but I gave it to you in a Newman projection? All right? So let's try that. So here's the exercise I want us to do with Newman projections. I kind of drew everything at you already. So here, name the following molecule. Let's name this and we'll take a little break. All right. All right, try that. So it might look scary, but if you know how the numbering works, the circle works. You just have to know that there's 2 carbons in that circle, and then you can number the rest of the chain that way. Okay. So if anyone locates the parent chain, tell me how many carbons that is, and then we can start destructuring this into a actual Lewis structure. Okay. All right. Okay. So does anyone have a number? Yes, 11. Good. All right. So here's how I would do it. So let's number this. 1, 2, 3. All right. Notice here, this line extends to here. So I'm going to write this as 4. The back carbon, the circle, as 5. Okay. And then it goes to here. 6, 7, 8, 9, 10, and 11. Good. All right. So it might be tricky to try to name it this way. So what I would do is now redraw this as a skeletal structure. So draw a chain that's 11 carbons long. Okay. Man, I can't draw on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So let's put on some substituents. All right. What goes on the 4th carbon? Wait, did I draw too many carbons? Yeah, I did. All right. I heard bromine on 4. No, close though. It's actually the other carbon. So bromine's actually attached to the back circle. What carbon is that?
That's 5.
That's 5. So let's draw bromine right here. Sorry. All right. And at the 4 position, there's what? Yeah, so it's going to be boom, boom, and then boom and boom. Okay, good. All right. Then the only other substituent on there is what? Is there any other substituents we're missing? Methyl on? There you go. All right.
Is the other substituent supposed to be on the 4th carbon though, not the 3rd carbon?
Which one? Oh, yeah, you're right. Sorry. Thank you.
What is it again?
So, it's a propyl. So the common name is isobutyl, but we can name it through IUPAC too. Okay? So, at the 4 position, we have for let's number this again. It's a complex substituent, so we have to number it appropriately. 1, 2, 3. So 4, 2, what? Methyl. So, and then what's the parent name of that one? Propyl. All right. And then the rest here, we have 5 bromo, 8 methyl. All right. So this is the way we number it, right? If we numbered it the other way, it wouldn't have the lowest numbers. So this is the way to number it. All right. So let's combine everything here. So we get 5 bromo, 8 methyl, -4 parentheses 2 methyl propyl. All right, what's the parent name? What's 11? You remember? Undecane, thank you. All right, so that's the extent we could ask from Newman projections, really. So, nomenclature, know every, way we can ask it, and the ways I've shown it to you are pretty much all the ways I could ask it. Okay? All right, so there's are any questions? Yes, Mariana.
Where did the propyl come from?
Oh, this one right here? So if we look at this group right here, right? The longest chain is how many carbons? Anyone can answer. So the longest, this branch here, how many carbons long is it? 3, and that's why we call it propyl. Okay? So we can't just say 4 methyl propyl, and we can't just say 4-2 methyl propyl. That wouldn't make sense. So that's why we put in parentheses and do it that way. Okay? I think we just need a little more practice with this, and that's what today in lab is for. Okay? Yes.
Explain why the methyl propyl's on the 4th carbon, not on the 5th.
Oh, yeah. So remember in this Newman projection here? So 1, 2, 3. Can you see this dot? 4. So the 4th is the front carbon. But if we look at the And then the circle there, that's the back carbon. So everything coming off the circle is on the 5th carbon. So bromine, there's a bromine there, and there's an H there, and attached to the left is the rest of the chain. So that's why that one's the 5th. The 4th is the center of the circle, and we can see that the isobutyl group is coming off that the center of the circle. So that's why that's carbon 4. Okay. All right. Looks like film a break, bathroom break here, and then we'll jump into reactions. Our first kind of real reaction for organic. Okay.
Name and location of substituent became branch, then stem, the root is member of continuous carbon chains. And so this is the branch, so we have to like do the same thing.
Yeah. So this is
the branch.
you have when you have eclipse in your
Then you start by this numbering the name and location. That's why it's 2.
that costs 2.5.
And then the
And each of these
H
H's,
but since it's a branch, we go to
so
the
there's 2 over here. That's 2, right? Yeah, I mean like 2 methyl groups interacting. That's what it is. Yeah, so it costs this much energy to achieve this state.
Not the cycling, but the just more. We're not doing that. Never done those yet. But we took notes on so what do you
Oh, okay. So stagger, there's no. All the existing ones will be higher in energy than this. And that's because they're the atoms.
Oh, yeah.
And I think I got there.
Quiz today is on hybridization acid-base. Syndrome G. Andrea? Then we got not here. Honestly,
We have two types of two branches.
yeah. Yeah, so.
For the synthesis alkanes, we never really have, and it's optional, we never really have.
Yeah.
It's like,
Walls
Did
one,
you
yeah.
do this one
When there's two substituents, you would have to. Yeah. One row. One of all these tables. There's one. Oh, Marielle?
You got it.
Juliana? Juliana here? Okay. Oh, okay. Need.
Here.
Jacqueline? Good. Isaac.
Is this the study or something?
No, this is like a breakdown of nomenclature. And then
Okay.
yeah. So here is your isotope, or you can number this J. Yeah, no. So we do one methyl. So at 3, you have to use parentheses, 3 dash, parentheses, 1 methyl. Or if you prefer the common name, you can use that isotope. Yeah. No. So this is equivalent to that. So what you should have done here is put the double bond on the other side. You draw the same structure, but you just put the double bond in the chart.
Wait, say that again.
So you draw it this way, right?
Yeah.
Couldn't you just do the
That's
or the double bond on the other side?
Oh, okay. Sorry, we've done it in a double block on that side.
Yeah. Yeah.
After I'm done with the workshop, can you help me on some of the drawing homework problems from
Sure.
the last
Yeah, I'll
session?
stick around.
Okay, thank you.
All right, so I passed back your quiz. You can find it on your desk.
One question, sorry, before we begin. So for this one, I'm confused now. So from this point to here, so what would I put for like
Draw the carbon scissors.
1, 2, 3?
No.
No, 2.
No, 2. F.
Oh, so it'd be 3. You don't have to put dashes since they're not common. Or parentheses.
So 3 mouthful, 4
mouthful.
F. That's it.
4
Yeah.
F, okay.
That's it.
And then I didn't get my quiz.
Yeah, you did.
It's not on my quiz.
Your name.
Juliana?
I did. Where is it? I know because I handed it out. Where were you sitting? Next to Brad? Sorry, wrong desk. All right, guys. Thanks for sticking with me. Okay, so let's talk now about why we learned this in the first place. Reactions. Okay? Now, if you were like investigating properties of these compounds, you would become a physical chemist. Okay? Now, if you're interested in the reactions, you will be called a synthetic chemist, and you work in the lab basically making giant molecules of pharmaceutical, medicinal, I wouldn't say cultural, but industrial and socially society relevant chemicals. Okay? So, for alkanes, there's only 2 types of reactions. What's one of them? You should know one of them because we do this every single day. So what's the reaction called when I take an alkane, inject it with reactive oxygen as a spark, and I produce water and CO2? Combustion. All right, so for combustion, you should be able to write the reaction. Okay, so for example, here's an example. CH4 plus O2 gives me CO2 and water. Okay? All right, is this balanced? No. All right, so for combustion, if I give you any alkane, you should be able to write and balance a combustion reaction, okay? And it's pretty straightforward. Your products are always what? Yeah, carbon dioxide and water. So they'll always be something like that. So if we balance this, I think this is it. We're done. All right, it won't be methane. That's too easy. It'll be something a little more complicated maybe. But combustion is one of them. Okay. 2 is, we call this number 2. The other reaction we call that is radical halogenation. So what you do here is you take it's an alkane plus a halogen. Let's just use chlorine. You're going to use heat or let me just erase that. Heat or H. All right. What does H nu stand for? Remember? All right. So radiation. So you use light of some sort, okay, to drive a chemical reaction. So that's what the H nu stands for. It's just an energy source, okay? And the products you get are substitution, CH3, Cl plus HCl. All right, the more important one for us is number 2. So this is where I'll introduce reaction mechanisms, but I'm not going to do that today. Okay, so number 2 is most important to us. Number 1, that's a general use for it. There's really no steps to remember except for this generic reaction we just wrote. Alkane plus O2, CO2, and water. Okay? All right. Any questions so far? Yes, I wonder.
Should there be W2 for the O2?
I don't think. Oh, yeah, you're right. Thank you. I almost forgot. Good. I forgot about the CO2. So there's 4 oxygens. Good. Thank you for catching that. All right. Any other questions? Or I think I caught everything, right? Hopefully that wasn't. Yeah, this is what happens when you just rant here. Okay. But any questions about combustion? Or don't worry about the second one. We'll talk about that much later. Okay? So the reactions here, we have to talk about 2 different kinds of bond breakage. Okay? So how chemical bonds break. So we have 2 of them here. All right. So let's now talk about bond cleavage. All right. So bonds can break in 2 ways. All right. We probably know this one. So the first one is heterolytic. Bond. Sorry, don't write bond. Erase that. All right. So in this type of bond breaking event, both the electrons go to one atom. All right, so this is an example of an acid-base reaction. The base takes the proton, takes the H+, and the chlorine leaves with the all the electrons, gains a negative charge. All right, so we form an anion and a cation. Okay, so both electrons go to chlorine. All right, so notice the kind of arrow we draw. The arrow has a full, we'll call it a full like head of the arrow, you know, the head of the arrow and the butt of the arrow. The arrow is complete, has a full head arrow. Okay, now we have to differentiate that with homolytic cleavage, which is which we will focus on in this chapter. So I don't know if we ever saw this before, but this is when a bond breaks, but you're not forming ions here. So let's take HCl again. HCl can break in 2 ways. The way I just showed you and this way. Now the arrows are split evenly between both atoms, okay? So this is what we call a fish hook arrow. All right. Electrons are shared equally here. Well, we all can say it was the covalent bonding rate. Electrons are shared, but they're not often shared equally, right? Unless they're the same atom. But in this case, when we break this bond, sometimes it breaks evenly, and sometimes both electrons just go to one atom. Okay, so homolytic cleavage is the former. We're going to have the electrons now on hydrogen and on chlorine. So now we have an atom, 2 atoms, and no charges, no ions. Okay, so that's the difference. So we learned, so we'll see both of these processes, heterolytic cleavage and homolytic cleavage. So all those arrows I kind of been showing with the electrons moving, and on the homework for acid bases, you saw some of that. Those were heterolytic cleavage, where the arrows start from one place and they go to another place, right? In homolytic cleavage, you're going to have an additional arrow always because the electrons are shared equally and they're not stolen or transferred. Okay, so you have this case where it's a polar compound, and then you can also have a case where it's nonpolar, like an alkane here. Okay, so this will split like this, And now you have a molecule with an unpaired electron and a hydrogen atom again. So if it's not a single atom, we can't call this the CH3 atom. We call this a radical. And there's a radical in both senses of the word. Unfilled octet, and it doesn't obey the rule. It doesn't have an octet. It goes like a maverick or renegade. Okay, behaves often reactively beyond the norm. So radicals here, some radicals in biology are stable. They're used for signaling in your body, but some are just plain up reactive, and they can cause disease and cancer and all that. Okay, so a methyl radical is unstable. All right, so this is what we call a CH3 radical, methyl radical. All right, so we talked about now radicals. Now we have to answer the question, like, okay, how easy is it to form radicals, and how do we predict the stability of radicals? Okay, so we're going to talk about bond dissociation energy. But are there any questions about this notation here or format? Any questions? Okay. So when we draw arrows like this is what we call electron pushing. And that's pretty much the things we'll see when we write mechanisms. So it's important that you understand how this works, because it'll make going through mechanisms a lot easier. Okay? But anyway, let's talk about bond dissociation energy now. Bond dissociation energy. All right. So the notation here is d degree for dissociation energy, but it's a value of enthalpy. It's a kind of enthalpy here associated with breaking a bond. And the energy refers to the type where it's homolytic cleavage. So the electrons are split evenly between the atoms of the bond. All right, so there's a few factors it depends on. Depends on A, size of atoms. B, energy of orbitals. All right, and C, stability of radicals, okay, and atoms of the products. And what I mean by that is you look at the products of these reactions above here, it depends on the relative stability of those atoms, okay? But in most cases, we're looking at just the radical that forms, okay? All right, so let's go over the first effect here. So let's go over the size effect. So I'll give you some data to back this up. Size effect. All right. We have our delta H, and they're using kcals per mole. All right, so let's look at the trend on the second row from nitrogen to fluorine. All right, the amount of energy it takes to break this bond homolytically is 108. To break the water OH bond homolytically, that's going to be 119. And then to break the HF bond, that's going to be 136. So the trend here is that the smaller the atoms, the more overlap the orbitals have when they form a bond. That's why it's stronger, okay? And then the larger the atom is, the weaker the bond. And you can kind of think of this as the bond is longer if the orbitals involved with hydrogen are larger, Okay, and so nitrogen will be larger than oxygen and fluorine. So that's why it's the amount of energy it takes to break this bond is the least. Okay, and this is even more pronounced if we look at orbitals. Okay, so size effect, we can see as we're going across the row, the smaller the atom, the stronger the bond. And in this case, we're comparing H and the atom X, nitrogen, oxygen, and fluorine. All right. Next, the effect of energy of orbitals. Okay, so let's just draw a few of them first. So we're going to have first an s orbital and the small p orbital of fluorine. So this would be an HF bond. Okay, the energy here, like we saw before, 136. So here it will be delta H. All right, now let's do Cl. So the H atom is the same size. The Cl is going to be slightly bigger than fluorine. So we have HCl. And you see here the bond is going to get longer here. So that's why it's weaker and easier to break. All right. Now let's look at bromine. Bromine has a small s atom, and then bromine has a large p orbital here. And you see the H bond to bromine. It's probably going to get longer there, and that's 87. So fluorine uses its 2p orbital. What about chlorine? Which p orbital is that? All right, it's longer, right? So it must be 3p. And then bromine, 4p. Okay? All right, then the last one we'll look at, iodine. So iodine's it's humongous. It's like this. So iodine here. So the bond here is the longest. See that? Longest bond here. Iodine uses the 5p orbital. And this energy is 71. So iodine has the weakest bond, easiest to break. Okay? All right. So that's the size effect. And now we have the effect of orbitals. Okay? So we see here, the bigger the orbital, the longer the bond. And that's why it's weaker. And size is pretty much the same argument. Weaker overlap, weaker bond, so easier to break. Okay? You can also think of it in terms of electronegativity too. More electronegative, whole bond is more ionic, stronger, harder to break. Okay. Now let's go over the effect of the stability of radicals and what that means, okay? And we'll talk about how we rank stability next time. So effect of stability of radicals. All right. So we're going to have here delta H. Again, kcal per mole. And over here we're going to have type of radical. All right. So first we have H3C. All right. So if we break this bond homolytically here, we will get methyl radical plus hydrogen atom. Okay. So the amount of energy this takes is 105 kcals. So that's a lot. Okay, and this is a methyl radical. All right. Then we have some other radicals here, namely ethane. So let's do CH2. And this is the other H to the carbon. All right. This breaks And this goes back to that carbon, and we get CH2, CH3 radical plus H atom. All right, this one is 101 kcals per mole, so not that different. And the type of radical here, so the radical is on what type of carbon atom? Primary, secondary, tertiary? What do you guys think? So we look at the carbon on the left there. How many carbon atoms is it attached to? 1, right? So this is primary. All right. So you might, so there might be a question like, are different primary radicals different in energy? The answer is no, not really. Okay. So let's say we have propane, and in this case, which one should I do? Oh, okay. Yeah, okay. All right. So say we have propane now, and we're looking at this H, all right? Boop. All right. So it doesn't matter if you have more carbon atoms or not. The radical is still on a primary carbon atom. So the energy actually doesn't change. So it's 101, and it's still primary. Okay. All right. So it looks like the more carbon atoms we have attached, it looks like the trend is going down. Let's see if that trend stays that way for secondary and tertiary. All right. So now we have a tertiary alkane, CH3, 2, CH. H. All right. Now this H and this carbon will now split, and we get CH3 2 CH dot plus hydrogen atom here. Okay. And now this energy goes down by 3 kcals, or 2.5 kcals to be exact, and this is secondary. All right, so it looks like the trend is still going down. So let's look at tertiary. And we can't go further than tertiary because the hydrogen atom is the easiest bond to break. Okay, it's harder to break a carbon-carbon bond. So that's why we don't see much of those types yet. All right, so the arrows go like here, and then we get CH3 C dot plus H dot. So these energy values, H, you're always generating H atom. So what we're looking at is the carbon radical here. Now this goes down in energy, 96.5. So this is almost 10 kcals less than a methyl radical. So this one's the most stable. 3 tertiary radical. Okay. So what we can say here is that the less energy that's released, that means the radical here is the most stable. Okay. And the more energy, you have to put in, that means the radical is the most unstable because you had to put that much energy to get to that state. Okay. So what we can say here is the relative stabilities. Okay, so relative stability of radicals. Okay. Sorry, let me just insert, let's be specific here, of carbon-based radicals, okay, of carbon radicals. All right, tertiary is the best. Secondary is in the middle. Primary and methyl are the worst. Okay, primary and methyl are kind of similar, but barely, but just by barely. Okay, so we'll just talk about why this is. next time. Okay, but now let's clear our desks, put everything away. I'll pass out the quiz.